Hello everyone, I am Amit K. Jain, working as Assistant Professor in STM Institute of Technology, Ujjare. In today's Control Systems session, we will learn a topic in relation to Module 5, State Variable Analysis. And the topic is Introduction to State Variable Analysis. So, what are state variables? A set of variables which describe the behavior or state of a system at any given instant of time are called state variables. Let us understand state variables with the help of an example. Consider an automated car. Now, behavior or state of the car herein is whether the car safely takes you to the destination in time. Let us assume that you are seated in an automated car. What do you think are the variables which contribute in determining the behavior of the system? Remember that behavior herein is whether the car safely takes you to the destination in time. So we have traffic conditions, environmental conditions, road conditions. These are some of the external variables over which you have little control. Similarly, engine conditions, fuel efficiency, speed, sensitivity variables. These are some of the internal variables which together will affect the behavior of the system. Apart from this, there are many more variables which you can control in a car, such as accelerator position, braking system, gear system, AC system, steering wheel, sunroof, and many more. Let us consider that there are n variables. All these variables in some way or the other will affect the behavior of the system. Now, at any given instant of time, if you are required to compute all these n variables to determine the behavior of the system, it would become very complex, right? Hence, out of all these n variables, we choose a minimal set of variables called state variables, which along with input can determine the behavior of the system at any given instant of time. Here, in this particular example, we can select speed, direction, and distance traveled as state variables, because if we know the speed and direction of our course of travel along with distance to travel, we can easily determine behavior or state, that is whether we will reach safely in time to the destination. Now we have an idea about state variables. Let us define state now. State of a system is defined as the minimal set of variables, that is state variables, whose knowledge at t is equal to 0 along with input u of t known sufficiently for t greater than 0, that is for all the time, completely describes the behavior of the system. To put it in simple words, state is nothing but a combination of state variables and input through which you can completely describe the behavior of the system. State of the system at t is represented as x of t. Some of the basic properties of state are: future output depends only on current state and future input. Future output depends on past input only through current state. State summarizes effect of past inputs on future output, just like the memory of a system. So to understand these properties, again we will look at an example. A rechargeable light. Here the state is the current state of charge of the battery. If you know current state, then you need not know how that level of charge was achieved to predict the future performance of the flashlight. But to consider all nonlinear effects, you might also need to know how many cycles the battery has gone through. But key point here is that you might expect a given linear model to accurately model the charge depletion behavior for a given number of cycles. But that model would typically change with the number of cycles. Let us look at a general example in the next slide to add more clarity to the definitions. So now let us take the example as state of your mood. Most of the times we say my state of mood is happy, sad, and so on. Here, state represents your behavior expressed in terms of mood. Generally, state of your mood may be happy, sad, which depends on n number of variables. There is a general perception that mood at the morning will carry over for the entire day. We all have experienced that, right, at some point in our life. Hence, your future state of mind, that is behavior, can be predicted by knowing mood at the morning. Now, how to determine the state of mood in the morning? It may depend again on n number of variables like experiences you had the day before at workplace, home, and so on, expectations from you and of you for the present day, and so on. But there is a saying that fresh day, fresh start. Generally, to be happy, you need to be both physically and mentally fit. In order to be physically fit, you may go for a jog, opt for exercise, or play games. Similarly, in order to be mentally fit, you may opt for yoga, meditation, listen to music, and so on. So, in this particular example, we can conclude that in order to determine the state of your mood for the entire day, we can have a set of 6 variables: jog, exercise, games, yoga, meditation, and music. If it is too much, we can water this further down to a set of 2 or 3 variables. So if you carry out these activities in the morning, during the course of entire day, state of your mood will be happy. Of course, it also depends on the input, that is situation which arises at a particular time. But you will be able to handle any situation with a calm mind and thus be happy. So with these definitions and understanding, let us explore more on state variables. The textbook definition for state variable is: it is one of the set of variables that are used to describe the mathematical state of a dynamical system, which we have already seen. And these are some of the properties of the state variable. That is, if you know state variables, then you can easily describe the behavior of the system at any given instant of time. Both of these points say the same. Now we will look at state vector, a vector whose elements are state variables. Similarly, state space, n-dimensional space whose axes are state variables. Again, we will have a more clear understanding of state vector and state space when we solve problems. Now we will look at limitations of transfer function based approach. Now here I will indulge on some history. See, now until now whatever we have studied, Bode plot, root locus, polar plot, Ruth criteria, signal flow graph, block diagram reduction, they were all transfer function based approaches, right? So all these approaches come under classical control theory. Now these transfer function based approaches had some limitations. So that limitations have been eliminated in modern control theory, that is your state variable analysis. So first we will look at the limitations of transfer function based approach. Applicable only for linear time invariant systems, applicable only for single input single output systems, design of solution is complex, possible to implement with zero initial conditions only, difficult to implement as part of digital design. So now here you may have a question: what is a linear system, what is a time invariant system, what is a single input single output system, what do you mean by zero initial condition? So we will look at all this. So now initially we will look at linear system. See, here we have a system having transfer function h or an operator h. So we will provide an input u and we are expecting an output y. Now for the same system, or with for the same system having the same operator, we will provide input as u1, and what is the output you are expecting? y1. This is the general system. Now for this general system, we have provided input u1. So next what we will do is we will provide the input as u2, and what is the output you are expecting? The output you are expecting is y2. Now again, for the same system having the same operator, if I provide the sum of the inputs, that is u1 plus u2, if you get the response as also the sum of individual responses, that is y1 plus y2, such a system is called as linear system. So this is called as principle of superposition. Any system which obeys principle of superposition is called as a linear system, and if it does not obey the principle of superposition, it is called as non-linear system. Now again, we will look at an example. The example we are talking is multiplication by a constant k. So again, in this system we are multiplying the input by a constant k, so the output will be k into u. So in the first instance we are providing input as 3, so what should be your output? y1 is equal to 3 into k. In the second instance we are providing input as 5, again here this should be k, read h as k here, so what should be your output? 5 into k. Now if I provide the input as a combination of the inputs 3 plus y, principle of superposition states the output should also be the summation of the individual responses, that is 3k plus 5k. Again here I will be getting the same output, right? So this particular system, that is multiplication by a constant, since it obeys principle of superposition, we can call that as a linear system. Next we will look at time variant and time invariant systems. Now here you have a thermal power plant. In thermal power plant you will produce electrical energy, and again you have a nuclear power plant where also will produce electrical energy. Now here the electrical energy produced does not vary with time. So systems where the output will not vary with the time are called as time invariant systems. Now let us take one more example, a solar power plant. Now do you think in a solar power plant the output will not vary with time? It will vary with time, right? Because during the morning we may get more power. As the intensity of sunlight decreases, the power produced will also decrease. That is, the output from a solar power plant will vary with respect to time. So this is a classical example for a time variant system. So this is regarding linear system, non-linear system, time variant and time invariant system, and these are the limitations of transfer function based approach. Now we will look at the advantages offered by modern control theory, that is the current topic, state variable or state space analysis. Again, applicable for both linear and non-linear systems, applicable for both time variant and time invariant systems, applicable for both single input single output and multiple input multiple output systems. Most of the times in real life we will have multiple input multiple output systems. And design of solution is simple. Now can you guess why design of solution is simple? Because we are considering a minimal set of variables, right? So obviously the design of solution will be simple. And then initial condition need not be always taken at t is equal to 0. At t greater than 0, at any instant of time you can consider initial conditions. And if you are planning to implement your design as part of digital design, then it is better if you go with state variable analysis. So this is about introduction to state variable analysis. Again, if you have any doubt, feel free to contact, and once again thank you for your time.